Yes, sorry, I'm in a noisy area, but I had to make that video. So this is the first diagram in the general purpose. So he told me to touch all the diagrams. So I'm going to go through the diagrams, then you compare with the notes app. I think I'll also try to go through what they said earlier to reconcile with the diagram. So now this is the first diagram of concerning the general purpose register. So now, and I mean the general purpose input output, yeah, the GPIOs, that's what they abbreviated. So and here we have two dealerships. One is this one, and the second one is this one. I want to label them with numbers. So now here we're trying to make to set this one into an output, right? So the second dealer down here that's labeled 2, what you should know first is that it stores whatever our output will be here. And remember, since these are D latches, each of them store 1 byte. We should first reconcile that both D latch 1 and 2 store 1 byte. And this one, it's usually called port X bit. Okay, X is usually to cater for. Remember, there are very many ports on the Atmega. There is port D, port C, and port B. So there they put port X because they were just giving a general scope. We don't know what port it is. So it should be like port B, bit. Now bit is like the remember bits in programming. Computers store values in 8 bits and usually use from index 0 to 7. So yeah, it could be like port C, bit 0, that means like the first bit, since our Atmega stores our computer store values in 8 bits. So what that already tells you that actually in real life would have like 8. If you want to store 8 bits, that means in real life you have like 8 D latches. Like, are you seeing where this D latch 2 is? So that means in real life we have 8 of them. That's what you should first know. I'm trying to give the general overview, and I'm going to go down. So now if I'm to go down, now here we have our our pin here. Our pin is on port X on pin A, like pin N, bit N. So that means this should be like, let me say port C, uh, pin. So remember our Atmega usually has 8. So usually our art maker has our ports usually have 8 pins. That means they can store 8 bits. So that means if you're seeing pin N, that means in actual sense a port will have eight pins, and that means each pin will be corresponding to one D flip flop. That means it will be outputting or inputting 1 bit at a time, because you can see a correspondence here of pin N, bit N. So yeah, if you can see that correspondence, how they correspond, that means this pin corresponds to 1 D flip flop. That means in real life there would be 8 of them to store 8 bits. So now that is that. So now I'm going to explain now these triangle looking things. So I'm also going to label them 1, 2. Then this one, let me put that 3 here. So now these that are labeled 1, 2, and 3, these are called tri-state buffers. Now a tri-state buffer is a circuit, like think of it as a switch. Now remember, a switch usually has the on and off. So now think of this. You want to, let me say, connect this line to this line. Let me say you want to connect them, like, remember how current works. You want them to connect to form like a switch, so that switch is closed for current to flow from here or this side, whichever direction, but as long as the circuit is completed. So now the the line up here that's on all of them, you can see on all of these tri-state buffers, if you look at 1, 2, and 3, now that one is like the switch. It's the one that usually turns them on or off, like completes the circuit or disconnects the circuit. So that means, so when a zero, like let me say, if you don't mind where it's coming from, I'll explain that. I'm saying, like, if there's a zero from anywhere on this line, that means here it's open, like this circuit is open. Then when it's a one, that means this circuit will close. Remember, this is a circuit. So as long as there's a zero on this line, this will open. As long as there's a one on this line, then the circuit will close, like to become. That means when it's a one, that means current can flow from here to here. When it's a zero, nothing can flow. A circuit is broken. So now, how does this work? Now, to make this pin an output, this pin here, make it an output. Uh, so if I'm to go back to the logic of outputting something on this pin, that means now we have these two tri-state buffers. In fact, there are three. But then now what you want to know are this DLAT. Its name is DDR, which is the data directional register. Now that one determines the direction of the input from you, whether this is an input or an output. So direction here they are talking about, like if it's an output, that means will be flowing, going this side for output, right? Then if it's input, then the direction will be this side, right? So now that's a responsibility of this DDR, something that determines the direction that you are going to flow into. So for that matter, so now if you remember what I told you about the tri-state buffers, that if there is a one, it closes, right? If there's a zero, it opens. So now this DDR stores, like in computer, store 1 or 0 bits. That's how they work. So that means here we can either store a 1 or a 0. But you can see that from our dealer to this line, continues and connects to this what? To this tri-state buffer. So that means whatever is in here, whether 0 or 1, will determine how this tri-state buffer behaves. So in this case, if you write a 0, so then since we want, now remember, now this one's called I think it's called a data register. Yeah, this one, the second deal is called a data. Let me put on there. Now this one is called a data register. This one stores the data I want output, so that which is either 0 or 1. It's called a data register. And if you look at this circuit, we want whatever is in here, goes for an output, we want data to go from the Atmega to output from our microcontroller to outside, right? That means whatever we store here, we want it to flow to this pin. But there is a hindrance here, because there's a circuit here that has to be complete for this to enable for movement of a bit from here to come here. There's a tri-state buffer, and of which this tri-state buffer is controlled by this DDR. So from what I've been explaining, that means for us to make sure that this circuit is complete for this bit to flow from here to be read here, that means the circuit is supposed to be closed, right? So from that, we realize that a 1 has to be written here, because when a 1 is written here, that the buffer closes, and when the circuit is complete, meaning whatever is here can be read here. So that's basically how how the the DDR works with the data register. Now, these other tri-state buffers 1 and 2, this one, just remember, whenever you programming, the computer wants to know what's happening. Like you want to keep track of what I like, as you can see, if I look at this data bit, like there's a data bus, and like what I told you guys last time, or what you should just know is that all bits, a data bus is a pathway for all bits. Like whenever I want flow of information from anywhere, all the bits be moving on the data bus. So that means if you want a one, you'd have to pick a one from here and put it here. If let me say you want a zero, you pick a zero from the data bus. The data bus like the source of information. Like should I say information is like a stream of bits that just like a river of them. So it's you choosing what you want. So now let me say, because a DLASH from architecture has two inputs, right? Now this first input where the D is where like the data enters from. Like when you connect, that means this is like an input to the DLASH. Now this other line here is what controls, like think of a DLASH as something that opens and closes. So when there's a command here, well, let me say that command could be one because it's not clear. It depends on how you program. Let me say that command is one. So if there's a one here, it could be like let the dealer store the value from the database. Then maybe when it says let the dealer to create, that means it cannot receive a new bit inside. Let me say you already stored the one here, it will keep a one there. So if I command it open again, that means I can feed in a zero and this other one will go out. Then I say let me close it. So that means the DLATCH will be closed. So that's how those two lines work. This one controls that the DLATCH is open to receive new content, and this one determines whether what input should enter, whether a zero or a one. So now realize our dealer here, let me say you've read, obviously a CPU will send like a signal from your code, open, receive a bit. And let me say it has received the bit one that's stored here. But then the PC has to confirm that actually a one that is stored there. Because what if there's an error, a PC requested for one to come here, but then actually a zero has entered here. Remember this from this slide, this is only an input line that CPU may not know. So there's this other side which is this other tri-state buffers which have, you can say they have read on them. All they do is enable the PC to read because no, this is like this is current flow. So when I connect here, I can be able to read what is here, right? That means the CPU can know whether actually if I center one here, so the PC checks here to see is it a one that's actually stored here. So these trusted buffers 2 and 1 are just like, should I say, confirmatory tests for the PC. So the PC here has a trusted buffer, it's connected. And you can see the command, like I said, bits only flow in the data bus, right? So that means when the PC, let me say the PC wants to confirm to read if what's stored here, it will send a signal because you can see a signal that controls this tri-state buffer comes actually from the CPU. This the signal, remember the top ones control the tri-state buffer is open or closed. You can see that this signal actually comes from the CPU. So in case the CPU wants to read what's here, it will send a one. Remember the one closes the circuit. When the circuit is clear, that means a bit will flow from here onto the data bus. Because remember that all bits only move on the data bus. So maybe that bit will travel somewhere. You can see this thing, and maybe the PC will read it off here to confirm that, oh, actually it's a one there. So that means whenever the PC wants to read here to make like a whatever is here to make a litmus test, it will just send a one here to be able to read what's here. So that's the same logic. That applies this tri-state buffer in case it wants to confirm that I want to write a one here to make this I want to write a one here to make this pin an output. So its litmus will be sending one here to read what's actually happening. So now this one is this line, all these tri-state buffers 1 and 2 are controlled by the CPU on it. Should I say the CPU does that when it feels right? Of course, you'd have determined that in your code, or usually it could also be inbuilt within computers to always just keep track in error detection. So now I think I've spoken about generally output. Now I'm going to scroll to input. So now this is the diagram for the input. Yeah, like I'm basically explaining the diagram. That's why it would be hard for me to scroll back to the notes and the diagram. So I maybe I suggest if you could go on the note side, you post the video and compare. So now this is the input, how the input works. But remember, from what I said earlier, if you want to, if I could just fast track through for you to know. So since you know there's a tri-state buffer here, so the first thing you have to know, there's a tri-state buffer here. Let me circle it. There's this tri-state buffer here. Remember, this tri-state buffer is one that controls what? It comes from our DDR. And from what I said from the earlier video, the data direction register controls whether whether data is coming in or going out. And in this case, you want input. Because before we're doing output to our data is going out, right? Now you want to do input. So for you to do input, you don't want output to be coming out. You want your microcontroller to be expectant. So that means you want to cut off this. You want to cut off this data register and that stores the data to be output. And then way you can cut it off is by opening this circuit. So then you can open this circuit, like from what I said earlier, as if whenever I feed a zero here, that zero opens this circuit. So now the basic thing you should know is that, oh, I want this circuit to be open. So when you open this circuit, it's by feeding a zero in here in this D latch one. Let me label them again. So the only way, if you want to, the only way to store a one here, I mean the only way to open this circuit is by feeding a zero in the DD in that D latch one. That's the only way you can open this circuit. So now you already know that now our circuit is open, like our circuit is open. So in this case, whatever is stored in our data register cannot flow here, because you know this data register determines whatever I want output. So that this cannot flow here. So we have cut it off. So now since we have cut it off, we have to find a mechanism of being able to store whatever is being input. Because remember, you have to store whatever is coming in. So hence this additional structure here. Now this structure down here is obviously, if I'm to go back to the tri-state buffers, from what I said earlier, on just help the PC to read. So you can see this one and this one and this one. They're just basically helping the CPU to read. But though this tri-state buffer down here, if I call it 2, now this one is not, this one is like, remember the top tri-state buffer, so then they're just like litmus tests for the CPU. But now this read down here is just for you to read. Like let me say you could have written a program. Let me say for one is coming in, when you read the one, do something. So now the read here determines in your code, maybe whatever you read determines what you actually do next. So now the reads up here, this read here and this read here are litmus tests. But the read down here on this tri-state buffer too, this one is actually designed according to your code, according to what your code does. So that means if there's a one here, do something. If there's a two here, do something. So okay. So now here our input comes in, obviously bits come in, let me say in serial, like in a serial flow. That means maybe a one card. Now you notice that here that D is here. Before it was DQ, but now it's D and Q. Because remember what I say, in a dealer receives from the D side, then outputs from the Q side. Remember, that's what we said earlier. So that means if you want to receive input only enters from the D side. And then remember, we said this other line controls whether the D latch is open or closed, right? And since data here, remember, obviously, maybe you're feeding in, let me say, a number. You're feeding in a number like 4. A number 4 can be represented by, are they 3? Okay, a number could be represented by three numbers in binary. So let me say 110 is flowing in here. So that means you're supposed to provide a way of let me because my RD that can only store one byte, 1 bit at a time. So that means when a bit comes, let me say bit one, you don't have a system clock. Let me say your system clock keeps opening and closing a delay so that other bits can flow in. Let me say a one comes here, read it off. Because remember, this is just current. Read it off, then uh, open the delete again for another one to come. Remember, you want that process to be continuous. You don't know how data is flowing, you know how much data is going in. So you want that process to be continuous. That's why it's connected to a system clock. Remember, system clock is like counting always, like open, open, close. So that is a continuous process. Like a one comes in here, read it, a zero comes in here, read it, another one comes in. So that's a continuous system. I want it to be very fast. That's why this D latches control is from a system clock. So basically, for input, if I'm just go through quickly, you write a zero here, open this circuit. When the circuit is open, that the data from here cannot flow to this pin. That means this pin is just awaiting to receive because nothing is on. Actually, no current is flowing here because the circuit here has been broken. Remember our bits, we're dealing with the electricity, so that's why I speak of current, because here we're dealing with the electricity. They flow in a form of electricity. So if the circuit is disconnected, they cannot move, because if they move, current is what helps the bits move. So that means if the circuit is broken, current cannot move. So that means you could say that this pin has nothing, like there's no current flowing on that flowing on it. That means the only current that can flow in it is external current. So when that external current comes with its own bits, it's stored within here. So now I think that's done. I'm going to go to the internal pull-up resistors.